All right, so let's look at checkpoint number 5 here. So, one of the big things we talked about this week was implicit differentiation. So that's what this first question is going to basically require of you. So I have a curve given by this equation, not a function, but we don't need explicitly defined functions to find derivatives. We can use implicit differentiation to find those slopes. Maybe. There we go. Okay. So how do we find the derivative of things like this? So, like always, we can take each term one at a time. So what's the derivative of 2x squared? That's 4x. This next term is a little tricky because now this is going to involve y. So one thing I want to be clear about here is that we are differentiating this whole thing with respect to x. 2x squared, derivative of that with respect to x is 4x. The derivative of negative 4xy is a little different because two big reasons here. We really want to treat this as the product of two functions. So one of those functions will be, let's say it's negative 4x. And the other one of those functions will be y. So let's use product rule here. So when we take a product, we use the product rule to take a derivative. We do the derivative of the first function times the second function. So what's the derivative of negative 4x? That's minus 4. And the second function we're going to leave intact. So that's negative 4y. Next, we do basically the opposite of that. I'm going to take negative 4x, leave that function intact, and then multiply that by the derivative of y with respect to x. So what is the derivative of y with respect to x? We have a name for that. We call it dy dx. So both of these terms right here are the derivative of that second term, negative 4xy. Moving on, 3y squared. This is kind of, we have to use the chain rule and implicit differentiation kind of, together here. So first we're going to take a derivative of 3y squared with respect to y. So that'll be 6y. But we kind of have to treat y as an inner function. So now we got to take the derivative of that inside function y. Again, what's the derivative of y with respect to x? We call that dy dx. So I think we're done now taking derivative of everything on the left-hand side of this equation. Next, we have to take a derivative of the right-hand side. Derivative of 3, that's a constant, so we get 0. So we're well on our way here to finding dy dx, but now we have to isolate it. Lots of ways to do this. I think the easiest way to do this, maybe the most direct way to do this, is get all the terms that have a dy dx attached to them, multiplied by them on one side of the equation, and move everything else to the other side. So I'll do this. Negative 4 dy dx plus 6y dy dx equals, and then I'll move the other terms over, 4y minus 4x. So now that I've done that, I can factor out a dy dx from everything on the left-hand side. Everything on the left-hand side has a dy dx. I definitely missed a term, didn't I? This is negative 4x. Yeah, negative 4x dy dx. So everything on the left-hand side will have a dy dx multiplied by it, because that was the way I decided to keep these things here. So they have that in common. So when I factor out dy dx, I have negative 4x plus 6y. And then that equals 4y minus 4x. So then our last thing to do here is divide to get dy dx alone. So then I get dy dx equals 4y minus 4x over, I'll make this positive, 6y minus 4x. So this right here is our derivative. You could probably simplify a little further by, all of these coefficients are even. So I could factor a 2 out of both and cancel, but totally optional. This is a good derivative. This is a good expression for dy dx. All right, part B, which is A. Part B, I want to find the equation of a tangent line at this point. So what do the equations of lines look like? They look like y equals mx plus b. What information do I have here? I think I have x and y because I was given that the coordinates of the point are 2, 1. So I have an x and a y. I don't have a slope. So what gives me the slope? So that is still the derivative. We think about one of the things we think about a derivative is it gives us the slope of the tangent line. So now let's evaluate this derivative. So m will equal dy dx at our specific point. So that's 2, 1. So 4 times 1 minus 4 times 2 over 6 times 1 minus 4 times 2. 4 minus 8, that's negative 4 over 6 minus 8, that's negative 2. So I get a slope of 2. So now I have that information. So now the last thing I have to do here is solve to get the y-intercept. So what's y? That's 1 equals the slope, which is 2, times the x-coordinate, which is 2, plus b. That gives me that b is equal to negative 3. So final equation here, y equals 2x minus 3. All right, good. And our final part here, I want to find 2 points on the curve where the tangent is horizontal. So what is, think back to, our life before we had to think about implicit differentiation. What does it mean when the tangent to a curve is horizontal? Well, if it's horizontal, it looks like this. It's going to have a slope of 0. So I can use that same reasoning here and say that dy dx equals 0. And I have an expression for dy dx. So 4y minus 4x over 6y minus 4x equals 0. What is going to make this equal 0? That's only going to happen if the numerator is equal to 0. So then I get 4y minus 4x equals 0. If I solve here, I get 4y equals 4x, or y equals x. So here's what I found. This is very important information. There are points on this curve where the tangent is horizontal, and those are going to happen precisely where, basically, if there are points on this curve where the y and the x coordinate are the same thing. So how do I find this? Basically, I'm going to take this y equals x constraint and use it in combination with the equation I gave you. So let's do this. Let's just write the whole equation in terms of x. So basically, since I know that y is equal to x, I'll just let every y equal x and see what I get. 2x squared, nothing changes there. There are no y's. But this next term is going to be negative 4x squared. So minus 4x squared. Plus 3y squared, or under these circumstances, 3x squared equals 3. If I combine terms, what do I get? 2 minus 4 is negative 2, plus 3 is 1. So x squared equals 3. What values of x is this going to give me? This will give me plus or minus radical 3. So now here's what I have. I have 2 points. One has an x-coordinate of negative radical 3. One has an x-coordinate of radical 3. So what are the y-coordinates? Well, remember that we found just a few minutes ago that the only places where I have horizontal tangents are where the y and the x coordinates are equal to each other. So realizing that, I get the y coordinates as well. So my 2 points are negative radical 3, and radical 3, radical 3. So that's all for question 1. Moving on to question 2. So we have a function here that describes how many catfish live in a lake, after it gets stocked, after it basically gets a population of fish gets introduced to this lake. So P stands for the number of fish that are in this lake T months after the lake was stocked. So question A, part A, how many catfish are living in the lake 9 months after they were placed in the lake? So 9 months, that implies that T equals 9. but what do I want to do with t equals 9? So for this question, I'm being asked, how many fish live there? That is what the function p describes. So for this question, I'm evaluating this function at t equals 9. So p of 9 equals 1,500 times 1.065 to the power of 9. And I calculated this before. What did I get? I got approximately 2,644 fish. And just a reminder, it doesn't really make sense in this context to round. You cannot have fractions of fish. So 2644, I believe, was the nearest integer to the whatever number this comes out with. So that's part A. Part B, what is that asking us? How fast is the catfish population increasing 1 year after introduction? So this is asking about a rate of increase. It's asking about a rate of change. So hopefully that evokes you to think about derivatives. If I'm asking about a rate of change, the thing about a function that gives me the rate of change is its derivative. So first thing I need to do here is take a derivative. So this is an exponential function, and if experience teaching this stuff is any kind of predictor, there are going to be a lot of you who look at this and think, all right, power rule, I can subtract 1 from t, bring down t, but that's incorrect. One thing I want to remind you of is there's a big difference between things that look like this, variable base, constant exponent, and things that look like this, constant base, variable exponent. This time we have a constant base. Basically, we have this thing, not this thing. So this is where we use our exponential function rules. So 1,500 is a constant multiple. I'm going to keep that off to the side. So what's the derivative of 1.065 to the t? So the derivative of any exponential function contains the exponential function. So 1.065 to the power of t, but then we have to multiply that by the natural log of whatever the base is. So times the natural log of 1.065. Do I have enough parentheses? Yeah. Actually, let's do this. Keep these things separated. So this is a good derivative, but I'm asking about a specific point in time. So I'm going to evaluate this derivative at what time? So 1 year after introduction, that'll be 12 months. Remember that time is expressed in months. So p prime of 12 will equal 1,500 times 1.065 to the 12 times the natural log of 1.065. And that's a value I found earlier, which is, if I round to the nearest integer, so approximately 201. What's a good unit for this? So this is a rate of change. This is the rate of change of, basically the rate of change of p with respect to t. So what is p measured in? That's measured in fish. And what is t measured in? That's time, and that's measured in months. So the population is increasing at an instantaneous rate of approximately 201 fish per month. All right, moving on to question 3. So the United States defense budget is given by this function over an 11-year span. So T is again measured in time. This time it's years after 2000, so years after our reference time. And B of T is basically our defense budget, and that's measured in billions of dollars. So part A, how much did the US spend on defense in 2007? So the year 2007, that implies that we want to use T equals 7. That's 7 years after the year 2000. But what function are we going to use here? I want to know how much they're spending on defense, which is exactly what B tells me. So for part A, I am going to evaluate function B for T equals 7. So 810 times the natural log of 0.7 plus 1.42. And this will give us a value of 608.6. So What does that really mean? So that comes out to be 608.6, and I'm going to put space in here because what this really says is 608.6. Is it $608.6? No, it's one thing to keep in mind here is this is billions of dollars. So our defense budget in 2007 was $608.6 billion, according to this function. All right, what's part B of this question ask? What was the rate of change of US defense spending in the year 2000? So rate of change, hopefully that indicates to you that I want a derivative this time. So how do I find a derivative of functions that look like this? So this is a natural log function. I have a constant multiple, that's 810. So basically I can carry that with me. But how do I take a derivative of a natural log? So the rule that we have seen is this: the derivative of a natural log of x is equal to 1 over x. Ours is a little more complicated, so we're going to have to use chain rule, but this right here will help me do like the outer layer of that chain rule. What's the derivative of the natural log of something? Well, it's 1 over that something. So 1 over 0.1t plus 1.42. But then the chain rule says I have to multiply that by the derivative of the inside function. What is the derivative of the inside function? This is linear, so that comes out to be 0.1. So our derivative is done, but let's clean it up a little bit. I'll combine the 810 and the 0.1 to get 81. 81 over 0.1t plus 1.42. So that's a good derivative, and I think that's as simple as we probably care to make it. But I want to evaluate this at a particular year. Again, 2007. So 81 over 0.1 times 7 plus 1.42, and that comes out to be approximately 38.2. But again, let's ask ourselves what units make sense here. So 38.2 what? So this is a rate of change. So what is B measured in? B is measured in billions of dollars. But B prime gives me the rate of change of B with respect to T. So B is measured in billions of dollars. What's T measured in? That is measured in years. So in the year 2007, our defense spending is increasing by about $38.2 billion per year. All right, that's all for checkpoint number 5.